This is Lab 5, Group 1. Our lab focuses on one of the most fundamental questions in physics, and that is, how does an object accelerate when it moves along an inclined plane? We will be using an air track and a glider to study this because an air cushion drastically reduces friction. That lets us observe motion as close as possible to the idealized condition described in our physics lecture, where the only significant force along the incline is the component of gravity that acts on the object going downwards. According to classical mechanics, especially Newton's second law, the acceleration of an object is determined by the net force acting on it divided by its mass. For an inclined plane, the lecture shows that the theoretical acceleration is given by the g sine of theta, meaning it depends on the angle of the incline rather than the mass of the object. This is why increasing the tilt increases the acceleration, while changing the mass of the object doesn't significantly affect the acceleration. Researchers have used air tracks for decades because it allows the observer, such as us or even scientists, to view these relationships with high precision. In this experiment, we will compare our theoretical acceleration predicted by physics to our actual measurements using a motion sensor. By adjusting the incline, we can see how the acceleration increases in predictable ways. And by keeping the mass constant or even changing it, we can observe that this has little to no effect on the acceleration in this system. This aligns with the broader scientific consensus that acceleration is independent of mass, a principle dating back to Galileo's early experiments. Understanding this phenomenon has real-world applications. Engineers rely on these principles to design roads, railways, ramps, and other forms of transportation. For example, highway exit ramps and wheelchair accessible ramps are built with a specific incline to be able to control acceleration in a safe way. Even roller coaster designers use these relationships to predict how fast or slow a cart will move with certain slopes. By studying a simplified version of these systems in our lab, we gain insight on how physics shapes the motion of objects in everyday infrastructure and systems. Now I will hand it over to my teammate Daniela, where she will explain all the materials we use in this lab and how we use those materials to get our calculations.
Hi, my name is Daniela Avila, and now I will explain the materials we used for lab number 5. For this experiment, we used several materials to measure the acceleration of a glider on an inclined air track and analyze the percent error between the theoretical and experimental results. First, we used an air track and a glider. The air track was connected to an air pump, which created a thin layer of air under the glider. This reduced friction and allowed the glider to move smoothly along the track, helping us obtain more accurate acceleration measurements. We also used small slabs made of metal to tilt one side of the air track. By changing the height of the slabs, we were able to change the angle of the incline and observe how the acceleration changed. Additionally, we used extra masses that were added to the glider in a balanced way. This allowed us to change the mass of the system and observe whether it affected the acceleration. To collect our data, we used a motion sensor connected to the capstone software. This sensor allowed us to record the position of the glider over time and create graphs such as position versus time and velocity versus time, which we used to calculate the experimental acceleration. Finally, we used a computer to run the capstone program and analyze the data obtained during the experiment. All of these materials were essential for measuring the motion of the glider, modifying the angle of the track, and comparing our theoretical and experimental acceleration results. So now I will pass it to my teammate to explain the procedure.
Hello, I will now be explaining the procedure for this lab. First, we will set up our air track. We will be given a couple of metal plates to put under one of the stubs. thus increasing the incline of the air track. We will then be using Pythagorean's theorem with the triangle formed by the table and the slabs to the line from the bottom of the single foot of the track to the double feet bottom. We will then use opposite over hypotenuse to get our sine theta, which our acceleration will be g sine theta. We will then use this table to input all of our calculations. On to our experiment development. We will set up our capstone to collect the data in a position versus time graph. We will then calibrate our sensor to see the cart from half the track up to the end of the track without any bumps. We will then have to run the graph until we get a nice U-shaped graph. And then we will get our initial velocity, final velocity, and experimental acceleration along with the percent error based off of this graph. In step 2, we will change the mass of the glide and discuss with our teammates. Are we experiencing any different acceleration? Why? Are we experiencing any different percent error, and why? We will then write down our predictions, reasonings, and consensus. We will then add extra mass to the glide on each side to ensure that it is balanced, and run the test again to get the initial velocity, final velocity, experiment acceleration, and percent error. We will then reflect upon these results and ask these questions. Are the accelerations different? Should they be that way? Why? Are the percent errors different? Should they be that way, and why? In step 3, we will now change the tilt of the track as we take off the slabs and measure our new opposite side. We will now calculate our new theoretical acceleration and its percent difference from the original. We can use any of the two glide masses, but it would be ideal to use the one with the lowest percent error. We will then plug it into this graph. For step 4, we will collect and calculate our experimental values and analyze the changes from our new setup. With this table, the initial velocity, final velocity, and acceleration 3 with the percent error with low tilt. Given the information from these tables, we will ask these additional questions. Which experimental acceleration had the most significant percent error? Which acceleration had the most unexpected value? I will now hand it over to my teammate Fernando, where he will explain the data and data analysis for this lab.
This is Alejandro for data and data analysis on Lab 5. For Lab 5, we were tasked to get a theoretical acceleration, an acceleration 1, acceleration 2, a theoretical acceleration 2, acceleration 3, and a percent error for each of our accelerations, and 2% differences. For the first part, we were tasked to find a different angle for the glide. In order to get a different angle, we added 1 centimeter worth of blocks under the front, which we converted to meters, which gave us a total of 0.01 meters. Using those numbers, we plug it into the law of sine, which is opposite over hypotenuse. For our opposite, it would be our height, which we had 0.01 meters, and the hypotenuse being 1 meters, which is the distance from where our test begins to our end point. We get 0.01. Using those values, we plug it into our theoretical acceleration formula, which gives us 9.81 our gravity times 0.01 our sine angle, which gives us a total of 0.0981 meters per second squared. Using that, we can run our first trial with 0 height difference, which we get a value of 0.41 minus 0.05 divided by 5.15 minus 1.2, which gives us a total of 0.091139 meters per second squared. For our second step, we now add the 1 centimeter or 0.001 meter height difference, and run the trial again, which in there we got the values 0.44 minus 0.12 divided by 4.3 minus 1, which gave us a total of 0.0969697 meters per second squared. For the next part of the lab, we're asked to get our second theoretical acceleration by having a different height and different angle. The law of sine is the same, with our hypotenuse being the same 1 meter, as our starting position does not change. Our opposite does change as we add more height to it, which we now have 0.015 meters. Plugging that into the law of sine formula, we get 0.015 divided by 1, which gives us a total of 0.015. Plugging that into the theoretical acceleration formula, we get of 0.14715 meters per second squared. For step 3 of the lab, we run a trial with our new height and different angle, which gives us values at 0.54 minus 0.10 divided by 4.55 minus 1.6, which gives us a total of 0.149. For the first part of our percent errors, we use theoretical acceleration 1 versus acceleration 1 versus acceleration 2. For the percent error on acceleration 1, which gives us a total percent error of 7.0958%. For the percent error on acceleration 2, which gives us a total of 1.15219% error. For the percent error on acceleration 3, which gives us a percent error of 1.36%. Lastly, for our percent differences, we use acceleration 1 versus acceleration 2 and acceleration 1 versus acceleration 3. For the first percent difference, which gives us a total percent difference of 6.397%. For the percent difference 2, gives us a total percent difference of 63.65%.
In conclusion, we're calculating our error percentage this lab again, only this time using weighted and unweighted data, as well as a flat surface, an inclined surface, and a taller inclined surface to get us different results, giving us different error percentages.